Hello everyone. In this session, I am going to discuss the detailed concept of losses in a transformer. We all know that the losses in a transformer are nothing but due to winding resistance we are having copper losses, and due to core we are having core losses, or they can call it as iron losses. So in this session we are going to, in this session as well as in the coming session, we are going to discuss the important observations regarding core losses. So first I would like to discuss copper losses. So what is copper loss? So these are the losses which are occurred due to what? Transformer windings. And the iron loss are due to what? Due to transformer core, right? So coming to first one, copper losses. The copper losses are simply I square R losses. We all know that this is the winding resistance in a transformer, right? So because of this winding resistance we are having a copper loss. So the total copper loss in transformer, before that the copper losses are I square R losses in a transformer due to winding resistance. So the total copper losses in a transformer is nothing but what? I1 square R1 plus I2 square R2. These are the losses before transferring, right? Before transferring. And these two are what? After transferring. And before transferring, this I1 square R1 which is present in primary, this is in primary winding and this is in secondary winding, right? This is present in primary winding. But coming to this is what? Referred to primary winding. Referred to primary means what? Transferring of a resistance from secondary to primary. Clear? Coming to this, refer to secondary winding. What is that meaning? Transferring of a resistance from primary to secondary. So at any case, before transferring and after transferring, is there any change in the copper loss? There is no change in copper loss. Before transferring, copper loss should be equals to, after transferring the copper loss should be equals. So these are the total copper losses in a transformer before transferring, and I1 square R01 referred to primary I2 square R02, where R01 and R02 are nothing but what? R1 plus R2 dash, which is equals to R1, R2 dash is nothing but what? R2 by K square. Like that, what about R02, which is equals to R2 plus R1 dash, where R2 and this is R1 dash is nothing but what? R1 into K square, right? These are the equivalent resistances referred to primary as well as secondary. So then how can we calculate the full load primary current and full load secondary current? Full load primary current as well as full load secondary current. So what is the equivalent circuit of a transformer? There is a load, right? This is the supply voltage V1, clear. So what are the currents? This is what? Primary current, this is what? I0, and this is what? I1 dash, and this is what? I2. So for us, this I1 and I2 are nothing but what? This I1 and this I2 are primary full load current, and this I2 secondary full load current. So In order to calculate the primary full load current, here the load is under full load condition, and this I2 is nothing but secondary full load current. And this, what is this rating? VA rating of transformer. The rating of transformer should be mentioned in, very important point, rating of transformer should be mentioned in kVA rating. What is the reason behind this? I will explain later. But the rating of a transformer is measured in, mentioned in kVA rating only. So what is this VA rating? These are this VA rating of a transformer and this EMF are nothing but what? Nameplate details. So this one and this, and this E2. So this VA rating of transformer and E1, E2 are mentioned on the nameplate details of a transformer. So if we have the nameplate details, so nameplate details. Let us take one example. A 20 kVA transformer and 2000 by 200 volts transformer. So these are the nameplate details. These are the nameplate details. These are the nameplate details. So this is the multiplication of E1 I1, which is equals to, we all know that transformer is a constant power device. Therefore, given data, E1 I1 should be equals to E2 I2 should be equals to what? What is the value? 20 kVA. So like that, what is the value of 2000 by 200? That is the transformation ratio. That is E2 by E1 should be equals to 2000 by 200. So E2 is nothing but what? Mutual induced EMF. E1 is nothing but what? Self-induced EMF. That is E1 and E2. Therefore, to calculate I1, how to calculate the primary load current? That is I1 should be equals to, what is the formula? E1 rating of a transformer by nameplate details of self-induced EMF. That is 20 into 10 cube by, what is E1? 200, right? What is E1? 200, which is nothing but ILV. What is the value of current? E1 I1 by E2 I2, which is equals to, I think, 100 amperes of current. Like that, what is the value of I2? E2 I2 by E2, right? What is the value of E2 I2? 20 into 10 cube by, what is the value of E2? 2000, which is equal to 10 amperes of current. So like that, you have to calculate the I1 full load primary current and full load secondary current. These I1, I2 are rated values which are not mentioned on the nameplate details. Only we have to calculate. We have to calculate this I1 and I2. The only mentioned details on the nameplate are nothing but rating of a transformer and induced EMFs. Rating of a transformer and induced EMF. These are only mentioned on the nameplate details. So if we have the data, obviously we are going to calculate the rated primary current and rated secondary current. So what is the formula of full load copper losses? That is PCU is nothing but copper loss. That's why you can represent with PCU, copper loss. So what is the formula? I1 square R1 plus I2 square R2, R, which is equals to what? I1 square into R01, which is equals to what? I2 square into R02. So from this, PCU is proportional to what? Copper loss is proportional to I1 square or I2 square. This is the copper loss is proportional to square of the load current. Square of the I2 is nothing but load current. So for a change in load, obviously the copper loss changes. That is, if load changes, PCU also changes. So for this, I would like to consider one example. Let us take full load copper loss as 100 watts. Then calculate copper loss at half of the full load. The given data is what? Full load copper loss is nothing but 100 watts. Then calculate copper loss at half of the full load. So copper loss in transformer at half full load is nothing but that is load is reduced to half, which means what? Load current is reduced to half. That is the meaning. For full load means what? I2. Half of the full load means what? I2 by 2. Therefore, copper loss in transformer at half of full load, which is nothing but what? What is the current? I2 by 2 whole square into R02, which is equals to what? I12 whole square by R01. So which is equals to what? 1 by 4 into I2 square R02, right? But the given data is what? Which is equals to what? I2 square R02, full load copper loss, which is equals to I1 square R01. So the copper loss at half of the full load is nothing but 1 by 4 into given data is what? 100, which is equals to what? 25 watts of copper loss at half of the load. So for that we have a formula, the copper loss at a fraction x of full load, which is equals to x square into full load copper loss. So example is what? At half full load x, which is equals to 1 by 2. What is that meaning? At 3 by 4 full load. What is that meaning? X, which is equals to what? 3 by 4 at 1 by 4 full load. What is the value of x, which is equals to 1 by 4? Okay, simple. Full load copper loss, let us take 100 watts. That at half full load, which is equals to what? 1 by 4 into 100, which is equals to 25 watts. Like that at 3 by 4 of full load, which is equals to what? 9 by 16 into 100 by using this formula x square into full load copper loss, which is equals to what? 9 by 4 into 9 into 25 by 4 watts at 1 by 4 of full load, which is equals to what? 1 by 16 into 100. They are going to get 25 by 4 watts. So like that you are going to calculate different values of copper losses at different fractions of full load. So What is that meaning? As the load current changes, the copper losses changes. These losses are called as variable losses. This is very most important point. What is that point? Load changes, or you can write load changes load current changes, right? If therefore load changes, load current changes. If load current changes, copper losses are also changes. Therefore, copper losses are also called as variable losses. Why these copper losses are called as variable losses? As load changes, load current changes. The copper losses are directly proportional to what? What is the reason? Since PCU is directly proportional to square of the current square, load current square. This is the reason. So this is very important observation. So in a transformer, what are the variable losses? The variable losses are nothing but copper losses. This is the clear-cut explanation for this. So next, iron losses. These are nothing but core losses. This can be categorized into what? Hysteresis losses and eddy current losses. We all know that hysteresis loss are due to what? Due to magnetic reversal of magnetic domains when we provide an external magnetic force. So this is the magnetization curve for that, and the hysteresis loss per one cycle should be equals to area enclosed with one hysteresis loop. Like that, hysteresis loss for given supply frequency, which is equals to area enclosed within one hysteresis loop into frequency. Just go through this theoretical approach. And in hysteresis loop, the height is determined by magnetic flux density and the width is determined by volume of the core, and the number of hysteresis loops are determined by supply frequency. And in order to calculate the hysteresis loss by varying supply voltage and frequency, this formula or this empirical formula is required to calculate different values of hysteresis loss for different values of voltage and frequency. That formula is called Steinmetz formula. Steinmetz formula. So where eta is nothing but Steinmetz coefficient and F is nothing but supply frequency, and here V is there, no, that is nothing but volume of the core, and here the X value is nothing but hysteresis coefficient. We all know that the hysteresis coefficient for silicon steel is nothing but 1.6. So during manufacturing we are going to change the eta value and the value, but after manufacturing means what? During the operation of the transformer, this eta value and volume of the core are constant only, which is proportional to what? P max power x and frequency during operation. So what is the value of x for silicon steel? The value of x is nothing but what? 6. So for x, which is equals to 1.6. Therefore, from this, what is the value of B max? Which is proportional to V1 by F power x into F, right? So hysteresis loss is proportional to V1 power 1.6 and F power 1 minus 1.6, right? So hysteresis loss is directly proportional to V1 power 1.6 and F power minus 0.6. So this is the empirical formula to calculate the hysteresis loss for different values of voltages and different values of frequency. So by changing different values of voltage and different values of frequency, what are the observations? What are the observations that we are going to discuss in the next session? But here the hysteresis loss is directly proportional to what? V1 power 1.6 and F power minus 0.6 for silicon steel. So next, eddy current loss. And these eddy current losses are due to what? Conductivity of the core. We all know that RC is nothing but resistance offered by the core, and IE is nothing but eddy current, which is directly proportional to the conductivity of the core. Like that, if the current is directly proportional to the conductivity, obviously the resistance is opposition to that conductivity. Therefore, by using I square into R, these are the eddy current losses which are directly proportional to the conductivity of the core. And how can we reduce that eddy current losses? By providing 5% silica to the steel, or by providing a laminated core. And for this eddy current losses, this is the empirical formula to calculate the value of eddy current for different values of frequencies and voltages. So where K is constant, Bm is nothing but magnetic maximum flux density, and F is frequency, T is nothing but thickness of the laminations. So during operation T, and one more thing, during operation thickness is T and K are constant, right? Only during manufacturing only we are going to change the value of thickness of the core, but during operation the value of thickness and the constants K are nothing but constants, right? So from this, eddy current loss is proportional to thickness square. So the eddy current loss is directly proportional to the thickness. That is, from this, frequency and what about thickness, which are directly inversely proportional, and frequency is inversely proportional to the thickness. That is, if we more the value of frequency, less the value of thickness. Okay, so more the design frequency of transformer, thinner will be the thickness of the lamination required. So these are the copper losses, hysteresis losses, and eddy current losses. The combination of hysteresis and eddy current, the combination of hysteresis plus eddy current should be equals to iron losses and copper losses, or we can say TCU, we can say TI. Okay, what are the units of power? Power units are what? Watts, right? That's why we have to notate with P or W, PI, WI, or PCU or PI or WCU. Okay, like that we are going to get different. This is WC. So copper losses are variable losses. These are going to vary for different values of load current. And these are the iron losses. WH is directly proportional to V1 power 1.6 and F power minus 0.6. Coming to eddy current losses, these are proportional to what? V by V, where V, you can write that point, proportional to Bm is nothing but what? V by F, right? Whole square. Where B is nothing but what? V by F, and F square into T square, which is equals to what? P square by F square into T square. F gets cancelled, therefore P square into T square. So from this, eddy current losses are directly proportional to what? V square only, supply voltage. We have to discuss these important observations in the next session. Thank you.